Hello grade 12s, welcome to my channel and hoping that you are doing great. So those who attended probably did gain some of their insights into this question paper, and of course it was noticeable that some of you were struggling with the network connections, so unfortunately it kept kicking you in and out. Either way, I decided to perhaps do this video to then supplement for those who could not get the full picture, but even for those who did get the full picture, to then have something to revise. So we saw how we worked through the MCQs, and we also worked through the organic chemistry component. So now we're going to focus on the inorganic chemistry, mainly doing rates of reaction, chemical equilibrium, and acids and bases. All right, so this is where we will start on this. So we will do the question. Why is it so thin? So this is question 5. Right, so given here is the information that the reaction of zinc and excess dilute hydrochloric acid. So it means zinc is the rate limiting reagent, right? Meaning that if zinc gets used up, then the reaction will stop, because hydrochloric acid is in excess. It means it always remains behind. So this is used to investigate factors that affect the reaction rate, and we know there's 5 of them. Now the student needs to know all 5, which is concentration, pressure when gases are involved. We need to know something like state of division. We need to know about temperature and a catalyst involvement. Okay, so these are the 5 factors that affect a reaction rate. So we need to know about them and we need to understand them fully. So the balanced equation for the reaction is zinc solid reacting with hydrochloric acid aqueous solution to form zinc chloride salt and hydrogen gas. Excuse me for that. Now, you know what I like to do whenever I see a reaction like this? I like to have it classified in terms of what type of a reaction is it, because many students do not even know what type of a reaction this is. And sometimes knowing this piece of information can actually help to answer questions much more adequately. Now if we look at zinc, its oxidation number is 0 in natural form. Hydrochloric acid is a plus, while the chloride is the negative. So we've got a 2 plus and a 2 minus because of that coefficient of 2. Right, so we go on to the other side. The zinc has paired with the 2 molecules of chloride ions. So basically it is a 2 plus and a 2 minus. And hydrogen in its natural state is perhaps Ganda, ne? Yeah. So what do we see? We know that an increase in the oxidation number of the substance as it crosses over to the product, that's called oxidation. And a decrease in the oxidation number, as we would see the hydrogen plus ions have decreased to 0. So this means this is reduction. So this then tells us we have a redox reaction. Right? Redox reaction. This is very important to know. Now, of redox reactions, which type? Because we have the spontaneous type and we may have the non-spontaneous type. So when do we decide which type are we dealing with? Then we consult our standard reduction potentials. Of course, we look at zinc, it's a strong reducing agent. But if we look at the hydrogen plus ions, they are quite a stronger oxidizing agent than the zinc ions, okay? So basically, this means hydrogen will undergo reduction. And the chloride ions here are the spectator ion, okay? Because these are weaker reducing agents, essentially. Right. So only chlorine gas is a stronger oxidizing agent, but chloride ions are a weak reducing agent. So literally, the reaction is between the zinc and the hydrogen plus ions. And this is the E cell. If we can calculate the E cell here, it is going to be positive, because this is how we would know that this is going to be positive. And if it is positive, it therefore means we have the spontaneous type of reaction over there. Now, if it is spontaneous, what does it tell us? It tells us that the delta H of this reaction is negative, because most, if not all, spontaneous reactions are exothermic reactions. Now, examples to these is spontaneous redox reactions, when we talk of the galvanic cell or the voltaic cell, and also acid-base reactions. You will notice that those reactions occur spontaneously at room temperature. So this simply says those are exothermic reactions, meaning the forward reaction is exothermic. All right. That's very important. Of course, it helps to analyze every little piece of information that is given to ensure that answering questions becomes quite adequate. Even if questions of higher order nature are created, you can be able to answer these easily. All right, so let's continue. The reaction conditions used and the results obtained for each experiment are summarized in the table below. We are told that the same mass of zinc, now this is the controlled variable, is used in all the experiments. Okay, good. The zinc is completely covered in all reactions. This means the zinc is going to react completely. There will be no part of the zinc that does not react. Okay, the reaction time is the time it takes the reaction to be completed. Of course, this is a bit of a definition, which in another question paper this may be asked. What do you understand by the term reaction time? It's literally the time it takes for the reaction to start and all the way to finish. Right, so this is very important. Now, we have a table. So whenever we've got a table or a graph, guys, we need to study that table carefully. Don't worry about the questions. I know many of you are taught to just jump around, look for information once the question is asked. This is what makes you fail, because you are not aware of anything of the nature of these materials or substances that are given beforehand. You need to be familiar with the stuff. It's like going into a new territory. You need to understand the territory before you can start, acting as a person who probably understands how things work there. You can't just figure out things as the necessity arises. Yes, some things can be approached that way. Remember, in the exam, we've got to balance time management and, of course, making sure questions are answered adequately. So it can be quite challenging. But at the same time, remember, this is you and I practicing, so you cannot rush through this. You've got to make sure your awareness is of the greatest nature possible, so that in the exams, even if you skim and scan things, you would be perhaps functioning at a better level than you would if you just continue this way from start to finish. Now let's have a look. Experiment 1. Using 2 moles per decimeter cubed of hydrochloric acid, a volume of 200 mils. Of course, here we know the acid is in excess, so the volume of the acid doesn't matter for us. The state of division of zinc is powder. We know that powder reacts much better than a solid form of zinc, right? Of course, when I say solid, perhaps than a ribbon, a zinc ribbon versus a zinc granules, or chips versus a powder. Powder will react much better than all the other forms. Now, this is at 25 degrees Celsius. This is 298 kelvins, right? Right. So, this is essentially the room temperature, if you think about it in chemistry, right? Yeah. This is essentially what would be a temperature that we consider room temperature in chemistry. So it already tells us this is indeed a spontaneous reaction. Now the reaction time here is 7 minutes. Okay, that's fine. We look at the second reaction. So in the second reaction, we see that the concentration has been decreased to 1.5 of the hydrochloric acid. But we still use the same volume, which in any case we don't care about. But we care that this is now zinc granules instead of zinc powder. So of course a lower concentration of the HCl and granules will certainly result in a slower reaction rate because of the concentration and the available particles here. So of course over the same temperature of 25 degrees Celsius. So this is indeed double the time that we got initially. So it makes sense. We go to the third experiment. We then increased markedly the concentration of hydrochloric acid while we used the same volume as in the first 2 experiments, and we used powder. So this means this compared to the first experiment, the concentration is high, but we're using powder as well as spontaneous, reactions at 25 degrees Celsius. And we saw that we took this one under 7 minutes, which is at 5 minutes. So this is expected to be this case because a higher concentration of the hydrochloric acid will then be able to react much faster with the zinc powder than a lower concentration of HCl for similar conditions. Right. We carry on. Experiment 4. We then got to this reaction. Of course, this one is comparable to experiment 2, 1.5 each. Right. Oh, I was hearing some noise here. Anyway, so we just increased the volume here to 400. But does it matter? The answer is not at all, because we know the acid is in excess, so we don't care about its volume. All we care about is the concentration, because it has a message for us. And we're using granules, so we decrease the concentration, we decrease the state of division of our zinc powder for the same temperature. So what happens here? If we look, we will appreciate that technically this experiment right here, this experiment, the concentration of HCl is the same as in experiment 2. And we used the zinc granules, and we're using zinc granules, same temperature as is here. The only thing that is a dummy here is this concentration. Is the volume, which we don't really care about. So this should be 14. That should take exactly the same amount of time as experiment 2, because this is literally experiment 2, but we added just an extra volume of HCl, and that doesn't affect the reaction rate, so it should be exactly the same. So again, this is a very good thing to notice. And then experiment 5, we've got a concentration of 2 moles per decimeter cubed of HCl, same volume as experiment 1, 2, and 3, and we're using powder, similar to experiment 1. But now what is of significant increase here is the temperature. So we've got a higher temperature at which we are operating. So compared to experiment 1, this is at a higher temperature, and as expected, we expect to have a higher reaction rate because of this higher temperature. Okay, so very important, guys, to work on the table before attempting to answer any questions, because once we understand that table, it becomes a lot easier to start answering. So 5.1 says experiment 1 and experiment 5 are compared. Okay, so we're taking this guy and this guy. So we saw that the only difference was the higher temperature. So it says write down the independent variable. So of course the independent variable is what changed, or is that which is changed, or what is changed. So what is changed becomes the independent variable, and what follows that change is the dependent variable. And of course the dependent variable here is the reaction rate. Great, so what is this? We changed the temperature, so it is the temperature. All right, temperature. Great stuff. So easy 1 mark over here. So 5.2. We are to define the reaction rate. Of course, guys, definitions. If you know them, good. If you don't, this is the chance to revise. Now, this means if you are not comfortable with the definition that you see right now, go and revise all definitions in this section, so that you are ready to tackle any question that may be related to these. Okay, so the reaction rate, we know that it is a change of the concentration of reactants and or products per unit time. Okay, so it's a change of the concentration of the reactants or products per unit time. Sometimes you may substitute the word concentration with the word amount. Now, an amount can be volume, can be concentration, could be number of moles, could be mass. So anything, essentially. So to be more general, I think it's safer to say amount. But since here we're talking about concentrations a lot, but there's also amounts of zinc here included, so it doesn't really matter. Of course, guys, get these things correct. So why do we say per unit time instead of saying per second? We cannot be specific because it depends on what time frame are we looking at. Are we looking at hours? Are we looking at minutes? Are we looking at seconds? Or even fractions of a second? So for reaction rate, we know that we don't really have a specific SI unit. It depends on the choice that the examiners give us. Hence, our definition stays as general as possible. And of course, for this, we get our lovely 2 marks. So 5.3. We then have to write down the value of X in experiment 4. Since we saw the comparison, we just write it. This is 14 minutes. Okay? Again, easy stuff here. 2 marks because it's a bit of a thought that is necessary to be comfortable with that answer. 5.4 says the Maxwell-Boltzmann energy distribution curves 4 particles in each of experiments 1, 3, and 5. So we're comparing Experiments 1, 3, and 5 are shown below. Now our job here, before we answer any questions, we need to identify which curve represents which experiment, right? Now if we look at experiment 3, we have a higher concentration of HCl molecules, while we have the same number of particles of the zinc powder, since we used the same mass. So the total number of particles in this experiment is going to be higher because of this concentration of HCl, but at room temperature. So we will see that the peak for B is much higher than the peak for A, right? But we can see that the temperature that represents the peak here is the same. This is what is important. So we will see that the peak here is of the same temperature, because remember, kinetic energy is temperature. So this EK right here is the same for each peak, but a higher peak means we had more particles. So this is definitely experiment 3, okay? Because there's more molecules because of that higher concentration of HCl. Of course, the zinc particles are the same throughout, so they each have the same number of zinc particles, but they differ in the number of the HCl particles, which in total will give us what we see. Great. So again, we see that they have the same average kinetic energy, because this is going to be giving us the kinetic energy of these particles. Okay, I'm going to talk to my sister a bit later. So now what does this mean? It means we need to know which ones of these two, 1, 3, and 5, have the same temperature. As we can see, at 5, we've got 25 degrees Celsius, 25. So those ones are going to be the same. If this is for experiment 3, then this one must be for experiment 1. So A is for experiment 1. And of course, C will definitely be experiment 5. Right. But why? We will see that whenever the average kinetic energy shifts horizontally to the right, this would be happening at a higher temperature. So we can see that the average kinetic energy of those particles in that experiment is much higher because it shifts to the right, and we can see the peak drops a bit. But again, the other issue that helps us to know this is the case, we will see that past the activation energy, we will appreciate the fact that the curve for C has a larger area under the curve for those particles with sufficient kinetic energy and already converting to products, because this is above the activation energy, which is what we see over here. Right. So at a higher temperature, this is what we expect. So this is very important, guys, to learn and to understand and to master. So please try to learn these for mastery. All right. So we've got 5.4.1, which asks, identify the graph A or B or C that represents the following. Experiment 3, we said that it's going to be B. Right, and the question says, give a reason for the answer. You can say that it has a higher peak due to more particles per unit volume, right? Since HCl used has a high concentration, right? So the peak here, or the average, is much higher because this one is because of it has a higher peak due to more particles per unit volume, since HCl used has a higher concentration, while they all have, here you can go to town, a high concentration, while all three have the same amount of particles of zinc. While they all have the same number of zinc particles. All right, so this is the one. I don't know why my writing man always just switches off zinc particles. Okay, of course, guys, for me, I always like to answer in full rather than to be cryptic, because if you learn to be cryptic, you're going to be useless. Believe me when I tell you. All right, so basically, the key part to this answer is the higher peak. And of course, trying to explain it is much more palatable than to just say a higher peak, so what? You understand? Try to avoid a follow-up question when you answer. Answer so that there is no follow-up question on that particular answer that you are giving. So of course, guys, we get a mark for choosing, and we get a mark for our comprehensive explanation there, which I believe all students should attempt to do. Okay, so 5.4.2. It says one that represents experiment 5. So that is C. Again, we need to provide a reason. So what can we say? Well, we can decide to describe the area under the curve past the activation energy, that it has more particles than it is, but I like that of the average kinetic energy as it shifts to the right. It's much better. So we can say the average kinetic energy of the particles has increased, seen with that peak which has shifted to the right. So we can say since the average kinetic energy of the particles has shifted to the right. As seen with a different peak, or should we say as seen with the peak, as seen with a peak or shifted peak. Right. So the average kinetic energy of the particles has shifted to the right as seen with the peak due, remember we need to explain why, due to a higher temperature of the reaction. You see, we need to be able to answer so that nobody asks, what the hell? So another person may say there's a greater area under the graph past the activation energy for curve C than the first two because of a higher temperature, where more particles will have enough, or should we say will have sufficient kinetic energy to form products. So again, this is a very nice one. Answer and explanation. But remember, as I said, when you give an account for something, avoid answering in a way that makes the other person to ask you another question to finally get the end of what you're talking about. Say what you mean nicely and completely so that you curb a second question in the same context, or should we say in the same issue. Right. So I hope you guys can see that this is how we answer questions. We don't faff around. Okay. Okay, so guys, that is the questions here. But of course, this thing is a bit crazy, so we move around a bit here. So there's 5.5, so this document was quite wide, so I need to make sure I don't leave questions unanswered. So 5.5 is saying experiment 6, which is not included in the table, is now conducted using a catalyst and the same reaction conditions as experiment 1. So again, what would be the independent variable here is the catalyst, because everything else is the same, right? Great. And of course, the dependent variable is going to be the rate of the reaction. So the question says, what is the function of the catalyst in the experiment? Of course, the catalyst lowers the activation energy, resulting at a higher reaction rate than experiment 1. So we will say it lowers the reaction, it lowers the reaction, no, goodness, it lowers the activation energy, goodness, what is this? It lowers the activation energy which required for the reaction, the activation energy for the reaction, resulting in a higher reaction rate than reaction 1. Can you see? We need to explain fully, guys. We need to explain fully. So what is the function? It lowers the activation energy. So what? So that the reaction rate is higher than it would have been if we did not add a catalyst. And of course, why would we want a higher reaction rate? Because we want it to finish soon. Because we don't have money to waste here, waiting and waiting. We want to get our products fast. The market is waiting for those to be sold. Okay, remember, these things are useful in industry, so it's not just fiction here. This is real stuff. All right, so how many marks were we getting here? Just 1 mark, of course, for the whole thing, guys. Remember, answer so that no further questions can be asked. Okay, this was 5.5. This is 0.1. Again, pay attention to the numbering so that you do not distort it. Okay, so we've got 5.5.2. It says, how will the heat of the reaction, okay, heat of the reaction, this is the enthalpy, delta H, in the experiment 6 compared to that in experiment 1. Choose greater than, equal to, or less than. So again, this is a low-key higher grade question, because how would you know what the heat is all about? And as you can see from our analysis, we saw that these are redox reactions. As you can see, classifying this reaction is actually key. So we know that the heat of this reaction is negative. And how will it change if we use a catalyst? The catalyst has nothing to do with that heat. It will be equal to. Nothing is going to change. The heat of the reaction is just fine. The only thing that is going to change is the activation energy that we need. But as for the heat, this is all good. All right, so mind you, the heat is the energy of the products plus the energy of the reactants. So it gives us the overall heat of the reaction. Okay, is it what I said? No, is the heat of the product minus the heat of the reactants. And so this gives us the heat of the reaction. So these ones, even though we may form them at a lower heat requirement, that is activation energy, but remember their heat is going to be the result, because every time molecules form, a bit of energy is released. So that would be the heat of the products, and of course the heat of the reactant molecules, because they need to gain some kinetic energy before they can combine to form new molecules, of course breaking older bonds, so to speak. So this is exactly the idea. So this one is not going to change, so it should be equal to. So remember this. Again, this is something to note. So it will be equal to. So we write as we are directed. Equal to, and that's it. Easy one, mark D. Again, you wouldn't know this if you did not know what this is all about, and you didn't know even how to look at the reaction involved as to what type of a reaction, and therefore what would be the heat of that reaction. So let's see. 5.6. Of course, this question also is classified under the higher grade questions. Stoichiometric calculations were essentially, of course, those of some higher order were essentially higher grade. In fact, this one, it's a standard grade, or at least what we would say fits both standard grade and higher grade. It doesn't look too complex for me to then put it as a higher grade question. All right, so what is the story right here? I'm going to answer this one here. So 5.6. We are then asked to calculate the average rate of reaction. See, we are told exactly the unit to use in mole per minute with respect to zinc. Okay, in experiment 2. Of course, we are given that we used 1,5 grams of zinc in this case. So of course, we need the number of moles of zinc. So we can say number of moles of zinc is going to be mass over molar mass. So this is 1,5 divided by the way, what is the molar mass of zinc? It's 65. Let me check. Sometimes the periodic table is necessary because you don't want to cram these things and hurt yourself. So where is the periodic table? Zinc is 65,4 on the periodic table that I see. So this may just be 65 rounded off to the nearest. So be very careful. So obviously, what is the answer here? We need the number of moles. So 1,5 divided by 65,4 gives us a 0,023 mole to 3 decimal places. Of course, now we want to do another calculation, so we need to separate it nicely. So the question is to calculate the average rate of reaction. So we know that the reaction rate here is going to be minus the change, because remember this is a reactant, so we need that minus the change of concentration of zinc divided by the time duration of this reaction. This is going to be minus into the final is 0 because zinc gets used up completely, minus the initial, which is 0,023, all divided by the time that it took for this experiment 2 was 14 minutes. So that was 14 minutes. So divide this by 14. Let's get our answer there. So we have here basically 0,023 divided by 14. So what we have here is 1,64 times 10 to the minus 3. Oof. Okay, let's just move things a bit. Let's just move things a bit. Okay, so this is don't know why I squashed myself here. 1,6 4 times 10 to the minus 3 mole per minute. Of course, guys, I'm squashing things now because I didn't give myself enough time, enough space. Maybe let me try to avoid something looking very bad here. Because I have to make sure, guys, that I do not let you present answers in the worst of ways, and you will go around saying that you saw it from me. Anyway, so that's the one, guys. It's refusing to really do what I want, but the question is answered and in full. Right, so this was an easy basic standard grade calculation. There was nothing tricky here. Okay, so basically finding the number of moles here is important. Writing the formula, substitutions, and the answer provided the unit is as it is required. If not, we lose the last mark. Of course, you can consult the actual marking guidelines to find out exactly how this is to be marked for this question. Either way, it doesn't really matter to essentially attach too much on how the marks are distributed in the actual memo, but what matters is to at least understand where marks are usually given, so that as you attempt to answer questions, you try your best to answer them in such a way that if you end up not getting the correct answer, the steps will justify you for some marks, as would be guided by the marking guidelines, of course. Right, so folks, that was it for those 15 marks. So it's usually around 15 to 20 or so to get, through this section pretty nicely. All right, so the question on reaction rates, guys, should not be a problem. Students must just master it. Okay, let's get to question 6, which is chemical equilibrium. So, question 6, we read carefully what we are given. Dinitrogen tetraoxide, which is N2O4 gas, decomposes to nitrogen dioxide gas, which is NO2, right, in a sealed syringe of volume 2 decimeter cubed. And we can see that syringe over there. So it says the mixture reaches equilibrium at 325 degrees Celsius. So this is already suggesting this is not standard conditions, is it not? So this is to suggest that the decomposition of dinitrogen tetroxide needs energy for it to occur. It does not seem to occur spontaneously. Right. So now we are told that this is reached at 325 degrees Celsius according to the following balanced chemical equation, and we see that the N2O4 is colorless while the NO2 is brown. Okay, great. So obviously if we needed energy, what does it suggest? Delta H here is likely to be greater than 0. Be very careful though. Don't overly insert your analysis into this, because you may be surprised that in the question it is said otherwise. But this is the understanding that if we look at that temperature and we look at what is cooking here, we saw that the gas that we put in the syringe was dinitrogen tetroxide, and now we ended up with a nitrogen dioxide gas, but at a temperature much higher than room temperature. So this meant we must have added energy here for this to even occur. Right. So this would suggest delta H must be greater than 0. So always, guys, any suggestion on the enthalpy change of a chemical equation, please ensure that you note it so that questions become much easier. Okay, it says when the equilibrium is reached, it is observed that the color of the gas in the syringe is brown. So this means this temperature change favors the forward reaction. Can you see? Now, this temperature already is a higher temperature, so an increase in temperature favors the forward reaction. This is indeed trying to confirm exactly our hunch that delta H here must be greater than 0 because it's already favoring the production of nitrogen dioxide gas. Now, of course, guys, standard question, state Le Chatelier's principle. So as we highlighted in the tutorial, you need 3 things here. One is the disturbance, right? Disturbance, which follows with a shift. And this shift must be the shift of equilibrium to cancel the effect of that disturbance. And the last thing, we need another equilibrium. Right. So how you structure your argument here is not a big deal. What matters is that we need to have an introduction of a disturbance or a change, and we need to see equilibrium shifting to kind of cancel the effect of that change. And at the end, we need a new equilibrium re-established. So this is if you forget the actual wordings of this thing, just remember these 3 things. I need to describe a disturbance, followed by the shift to cancel that disturbance, and a new equilibrium must be established. That's the essence of Le Chatelier's principle. So we will say it. So how does it, we state that it says a disturbance, when a disturbance is introduced to a chemical system in equilibrium, right? The equilibrium will shift so as to cancel the effect of that disturbance until a new equilibrium hayi wa my hand kanti utheni ngathi uzondibhalela inyongo nje. Equilibrium is established or re-established. Established. Okay, so this is the best way I can put it. Of course, guys, you can cram whatever you want to cram because you are told to do that anyway, so go for it. Cram so that you can become useless, because cramming doesn't help. Trust me, it makes you look good when you actually are bad. And the problem is that you'll be placed under pressure when all of this is over. So do yourself a favor, do the honorable thing, learn to understand and gain insight. And from that, you also develop skills so that when these things need to be put into perspective later on, you will not shake at all. Of course, guys, this is a cheap 2 marks because if we describe a disturbance, this is very important, and stating that the equilibrium will shift so as to cancel that disturbance, that's the 2nd mark. And of course, we re-establish a new equilibrium. So if those things are in there, we are 100% good. Right. So 6.2 says, the syringe is now dipped into a beaker of ice water. So what are we doing in essence? We are decreasing the temperature. Right. Now, what did we say? The forward reaction was exothermic. If we then decrease the temperature, it means we will favor the reverse reaction. So we will favor the reverse reaction. That is what is going to happen. Now the question says, after a while, the brown color disappears, meaning it turns to colorless. Or we say light brown if we want, because we're slightly getting colorless. So it disappears, and that means we really favored the reverse reaction. And remember, the reverse reaction, has been favored here by a drop in temperature. This is consistent with our delta H, because if delta H for the forward reaction is positive, it simply means delta H for the reverse is going to be negative, because that would be exothermic. So it says, is the forward, now the question is on the forward, is the forward reaction exothermic or endothermic? We know that we decided the forward reaction is endothermic. From just analyzing what we were given, we could almost tell this thing before we could even talk about this issue here. But now we are required to explain our answer using Le Chatelier's principle. So again, an argument using Le Chatelier's principle is in this manner. 3 things. The disturbance and its influence that we notice. And therefore, we talk about Le Chatelier. What does Le Chatelier tell us? So the second bullet should be about Le Chatelier's principle. And now this time we don't need to restate it or to say it nicely like that. We don't even need to even place the reference to say according to Le Chatelier, but that's what actually it means. We know that we would talk about a temperature drop favoring a particular reaction. And which reaction seems to be favored here is that which we will see. And as a result, we make a conclusion. So again, we go in 2 steps here. 3 steps, stating the disturbance and its influence, and what Le Chatelier says, and identifying something, then drawing a conclusion. So it says, what is it? We said it is endothermic. Right? Endothermic. Now, what is the argument? The argument here is saying, number 1, we saw that a decrease in temperature favored the reverse reaction. Okay? So a decrease in the temperature favored favored the reverse reaction, right? This is noted by the disappearance of the brown color of nitrogen dioxide. Okay, you can even explain that seen with the disappearance of the brown color. Is it disappearance or fading? Let's just say disappearance. Seen with the disappearance of brown color. That's too much. You understand, right? Let's not go too far. So the reverse reaction was favored. This is noted by the disappearance of the brown color. 2. Now this is when Le Chatelier's principle comes in. This is where the principle is stated. What does Le Chatelier says? Remember, when we drop, remember that's a disturbance. How will the equilibrium react? It will try to increase that temperature, to actually oppose that disturbance. So we know that a drop in temperature or a decrease in temperature favors the exothermic reaction. Favors the exothermic reaction, right? Now, guess what? A decrease in temperature here favored the reverse reaction. So we can say the reverse reaction. The reverse reaction is exothermic. Therefore, the forward reaction is endothermic, right? So again, as you can see, we went about our business nicely. This is where the principle applies, and now we just try to logically make deductions and conclusions. All right. Of course, we have already made this conclusion up here. We just wanted to show how it comes about. So first, we said that's a mark for this. Now, a decrease in temperature here seemingly, or should we say it definitely did favor the reverse reaction. But now this is where the Le Chatelier's principle comes in. We get a mark for that, and stating that the reverse reaction is therefore exothermic because it was favored by that drop in temperature. Then we can make that conclusion because in an equilibrium situation, if the forward reaction is endothermic, the reverse will be exo, and vice versa. All right. So this is how a question like this, guys, is to be answered. Please note the attack that I have given here. This is how a question of this nature should be attempted. No matter what question comes, this is what we need to do to answer questions fully then. So again, an easy 3 marks. Always a question that is present in the exams. So learn how to answer it so that you just take marks, okay? 6.3 says the volume of the syringe is now decreased, okay? Now what happens when we decrease the volume of a syringe? What do? We literally increase pressure, right? Now we know that pressure affects the rate of the reactions and also can affect our equilibrium state here. Right, so what do we know? Pressure always favors the reaction with the increase in pressure always favors the reaction with the least number of moles. It favors the reaction with the least number of moles, okay? So this is very important to take note of, guys. Now we will see that if we increase pressure here, which one has the least number of moles? This is 2 against 1. Can you see? This is 2 against an invisible 1 over here. So this means we will favor the reverse reaction as well. All right, so this is very important. So in essence here, we will favor the reverse reaction. Now it says, how will each of the following be affected? Choose from increases, decreases, or remains the same. the number of moles of dinitrogen tetroxide, well, since we favored its production, it should increase. So we've got 6.3.1. We write increases. Okay, 6.3.2 says the value of the equilibrium constant. Remember, this one is only affected by temperature. Okay, only affected by temperature. So nothing else will change the Kc value. So a student of mine asked me a very smart question. Why does temperature affect the Kc value? I did not have a straight answer there. So what do you guys think, the audience? Can you share your ideas in the comment section? Why does temperature affect Kc and not others? So we'll say remains the same. Was it the same? Yeah, remains the same. Remains the same, right? Right, so 6.3.3 says the rate of the forward and reverse reactions. Now remember, pressure, an increase in pressure in this case, what will it do? It will favor the reverse reaction by making it faster, right? So it will increase the reverse reaction. But if the reverse reaction increases, automatically the forward reaction will also catch up to get to a new equilibrium. So this means they will both increase. So we'll write increases. Remember, pressure does affect the reaction rate as well. So good. So again, this question is quite a popular question. Well, perhaps it's a bit technical. So some proper understanding of how equilibrium works, and of course measuring reaction rates and equilibrium at times, as you can see here, is quite important as well. So it's quite an integrated segment of this topic. So this is again another issue that if you're not comfortable at this stage, you go back and read something about equilibrium and ensure that you've got it right. Try as many questions as you can find before you move on to the other topics to then get the essence of that topic. Right, so for each one we're just scoring individual marks. Nice. Now 6.4 is the big question, right? That everyone loves. Do you all guys love it? If not, you better start loving it. Okay, so we've got N2O4 forming 2NO2. This is gas. Of course, the states of phases here are very important. So I told initially X moles of dinitrogen tetraoxide gas were placed in the syringe of volume 2 decimeter cubed. Of course, this was stated already up here. So sometimes the examiners may not repeat this. So please pay attention. This is still the same question. So the volume, you might just need to keep it in mind. They were kind enough here to remind us. So when the equilibrium was reached, it was found that 20% of the dinitrogen tetroxide actually decomposed. So this is what changed, just 20%. Now, if the equilibrium constant Kc is 0.16, now this is where I have a bit of an argument with how examiners actually make these questions. For me, remember, at this temperature, we were told we had more products than the reactants, right? So that means this is a proper fraction, and not a proper but an improper fraction, because remember Kc is the ratio of the products. So this is NO2 in this case, but remember the coefficient is 2, so this is even augmented by squaring, divided by the concentration of N2O4. This is to the exponent 1. Remember, if the numerator is bigger, even if it's 0,005, then divided by 0,002. The answer here is going to be greater than 1. Okay? So this idea here, when we have more products in an equilibrium state, it means Kc is greater than 1. But look at the Kc these guys are giving us. It's less than 1. That's ridiculous. I don't know who writes these questions and why they are allowed to mess around with information. Because guys, these small little slip-ups create very bad impressions on students. And mind you, these are the future scientists. So if you don't already make it clear that the principles are the way they are and you keep bending them however you like because it's clear, the examiner just guessed a value. They forgot that they created a scenario that already told us Kc must be greater than 1. Because if we've got more products than the reactant, then we have an issue here. Because at this temperature, that is what we were told. But now, can you see at the same temperature, all of a sudden it's just 20% that has occurred. Now the question is, what the hell? What are we being told here? Now it means that brown color is not exactly brown, right? Perhaps it's light brown, I guess. It's a mixture of the two. I'm not happy with this because the Kc value, if we have more products then ideally, guys, you see, this is when you realize examiners themselves are just some special people. I would put it that way. They're just some special people because they get challenged by their own creations, which is great to see that indeed students should not be punished because even those that are supposed to evaluate them are themselves a bit lost. Okay, maybe I'm being harsh. I don't know. I don't care. Because if we're going to talk science, guys, I suppose we should expect something of the higher order from these people who actually create these question papers and those who get paid to ensure these are proper. Because now this is just suggesting we're paying people for nothing. Because if they cannot really keep up with the principles, remember guys, we cannot distort science, not even if we choose to. I know this is an exam, it's a hypothetical situation, but guess what? It mimics a real situation. So we cannot find ourselves wanting. Yeah, I am allowed to make those mistakes because who cares who I am? Nobody in the field of science. I'm not even a teacher for that matter. So I'm allowed to talk nonsense if I want and to babble if I have to and to go lost if I choose to. No one can hold me accountable for anything in this regard. Unfortunately, social media is unregulated. So there are no strict regulations on how people should actually post materials and stuff. It's only, the obvious and, for obvious reasons that we probably would not be allowing on social media. But the rest, come on, man, I'm just a babbler, a fanatic, so technically I'm not supposed to be correct. And actually I should be wrong and more wrong if I want. Anyway, folks, let's just leave the arguments. Let's solve the thing. So we will know that initially, number of moles, right? Yep. Change number of moles. Equilibrium number of moles, right? And then once we use square brackets here, automatically we mean mole per decimeter cubed because the square brackets mean molar concentrations. Small letter n means number of moles in moles, all right? So there's no need to write more than that if, of course, you are comfortable. But if you're not comfortable, you can do whatever you are told to do. But for me, this is enough. And anyone who tries anything is going to have to deal with me first before they can deal with my students. And I can take those people up and down and win shame them if they feel they can shame me. No, I would actually shame them. So please don't mess with my students. Wherever you are, however you feel about my students, please appreciate them. Those students have been fortified to be something way better. Just appreciate the help and let them flourish. Do not squeeze my students. We will have a serious fight. I swear to God. Do not tempt my patience in this one. Anyway, guys, that's just a threat, you see. So we're told this is X moles. Initially, there shouldn't be no nitrogen gas, nitrogen dioxide gas. Because at first we just put dinitrogen tetroxide and that's it. Now we were told only 20% changed. So 20% of X. Now what is 20% of X? This is 20 over 100, isn't it? 20 over 100, which is basically 0,2. So this is 0,2X in essence. Right. Now equilibrium is going to be 1 minus 0,2. It gives us 0,8X. Right. Right. Now at equilibrium, we know that the concentration is essentially, how many moles? 2 decimeter cubed, which gives us 0,8 divided by this is going to be 0,4X. Remember, X represents moles here, and of course per decimeter cubed. So we can just say per dm cubed. Okay, great stuff. And of course, folks, remember the change is what changes things. We cross over at the change. Now, if we changed by 0,2x, then we double this. It's going to be 0,4x, right? 1:2. Then on the reactant sides, on the product sides, we add 0 plus this is going to give us 0,4x. And the concentration is going to be 0,4x divided by 2, which would give us a 0,2x per dm cubed. So guys, this is very, very, very important to do. And this question is actually the simplest. I don't know why 8 marks were given here. It really looks quite simple. So we know that Kc is going to be the concentration of NO2 all squared because of its coefficient over N2O4 to the exponent 1. So this implies that Kc we're given is 0,16, which is ridiculous for the statement that we were given here. Doesn't make sense anymore. So the examiners are changing their own story. Anyway, this is fine. This is going to be divided by 0,4x. Of course, this is over 1, folks. So this would imply, what do we have now? So basically we cross multiply here. I thought we were going to finish this answer here, but now I'm feeling like it's not going to happen. So let's see, we will have 0,4 times 0,16. So what do we get here? We get 0,064x is equal to, now we got 0,2 squared. It gives us 0,04x squared. Right. So at this stage in maths, we can do gymnastics however we choose to. So you choose to be smart or to be weak. It's up to you guys. You've got all the tricks. I've taught you maths properly. So you can. I want to get rid of this 0,04. And I want to get rid of this x. So I'm going to divide by 0,04x. Now you can go about it the other way, transpose the other side, take the highest common factor and factorize essentially and solve. Honestly speaking, if you know the gymnastics, you will just be fine, because I know this one goes, I know this one takes the square, I know this one takes that one, and therefore I have my X value here. Right. So my X value is just going to be 0,064 divided by 0,04. Very simple. So this is 1,6. Remember, this is moles. Mole or moles, whatever. Right. Damn it, man. Yenza ntoni. Angiqheli. Iyangiqhela still. Okay, that's fine. Isangiqhela kanjalo. Thina siyiqibile. So this is good, guys. So we knew that X represents number of moles, so it should be in moles. Right, so this one was not a very difficult calculation, but as you can see, mathematics is involved here, quadratic equation specifically. So you cannot just, jump around here. So what is important, folks, I would believe that this change, to determine that change is key, and to find it on the other side is key. Each one of these concentrations is key. KC formula, key. Substitutions correctly, key. The final answer, very key. So this is 1, 2, 3, 4, 5, 6, 7. Well, the 8 story, I don't know. Perhaps it's the overall thing. It's an extra mark, I guess. Or we can say this portion here where we calculate the equilibrium number of moles for each. We can bunch that together because it's too simple. Right, so this is essentially, guys, how students should go about this type of calculation. And please do not make any mistakes. Pay attention. Make sure most of the stuff is done the correct way. Okay, so let's take the acids and bases question so that we can end this review for now, okay? Or perhaps we can push it a bit further. It is up to us. But what I like is to not overload students. So I'm going to do this one, stop, then take another series of questions of this nature, because these are the 3 major topics in chemistry that students fail to understand properly and so lose marks in them. Organic chemistry is quite easy. Most of the guys get marks there. Perhaps the other topic that is challenging is MCQs. But MCQs for chemistry are usually straightforward. 1 or 2 or 3 questions would be of a higher grade nature that demands some thought, that perhaps may leave you crying, because even when you see the memos on such questions, you just want to laugh. That these very people don't know what they are talking about sometimes. I'm not being negative though, but I'm just stating the facts. And sometimes you realize that the creator was literally not very clear on the topic, so they didn't do it well. But it doesn't matter, guys. We're all human. Part of making mistakes is what we are. Okay, let's quickly get through this question 7. Of course, guys, how many marks were we taking from that question in total? 16. So as you can see, very nice 16 marks there. Not so difficult. Okay, question 7. I'm a bit tired, so I'll probably do the other part that we did, because we did 2 extra questions on chemical equilibrium and acids and bases, and then of course we skipped the one on reaction rate. So I'm going to bunch them together for you guys to see. Then on our session tomorrow, we'll just try to tie up the knots, maybe sprinkle a bit of MCQs in, so that you guys are ready for everything, right? And maybe squeeze in an extra organic chemistry question so that we can have a discussion on that as well. Right, but that one is usually very, very, very easy. So 7.1. We're told sulfuric acid is a strong acid present in acid rain. It ionizes in 2 steps, and we can see those. This is quite a familiar stuff. So if you are a student in Matric, you should know this already, because over so many times in textbooks, study guides, past exam question papers, this is stated multiple times. So we go straight to the issues here. So we've got 7.1.1. We now need to define an acid in terms of the Lowry-Bronsted theory. You can say it is a proton donor. Is it a proton donor? Yeah, it's the proton donor, this one. You cannot say anything else. It's a proton. Is it a proton or is it a proton? Is it a proton or is it a proton? It's a proton donor. Donna. Is it Donna or Donna? Yeah, boy. It's a proton donor. Okay, let's speak properly sometimes. Okay, 7.1.2 asks us to write down the formula of the conjugate base of the hydronium ion, and we know that that should be Vater-Bas. No questions about it. If you also study well, you would know this. But how do you decide now? We will see that the HSO4 here goes into HSO4 minus, right? Now, what is the difference? The difference between the two is minus the hydrogen plus ion. That's how we tell these are conjugates. Of course, that being an acid, this is going to be a base, right? Same Konkolose. This one comes down to here. And as you can see, the difference between them is also minus 1 hydrogen plus ion. So usually these conjugates, what? A base and an acid, conjugate base and an acid, the difference between them is the 1 hydrogen plus ion. So, of course, we look at them on either side of the equations, from left to right and right to left, whatever you call it. So essentially, that means H2O, can you see it's 1 hydrogen plus less than the H3O plus. So that is the Vater-Bas, that's all. Kitchen. Now 7.1.3 says, write down the formula again. Here we were told formula, don't write water in words, formula. Write down the formula of the substance that acts as an ampholyte in the ionization of sulfuric acid. Can you see this is a specific question now? Remember, water is an ampholyte in general, but let's look at water here. It is accepting a proton. Water here is also accepting a proton, so it is acting as a base here. So don't write water. Now let's see what is happening. Sulfuric acid loses its hydrogen. This is an acid, and then it makes this dude, the hydrogen sulfate ion. But in this case, the hydrogen sulfate ion actually protolyzes water by giving it a hydrogen plus ion. So if it gives, according to Lowry-Bronsted, this is an acid. So can you see it is a base here and it is an acid there. So in this ionization situation, it acts as both a base and an acid. And so it is the ampholyte. So right here, HSO4 minus ion. Right. Great. So this is indeed a bit of a situation. So please, again, now what are the highlights over these first 3 questions? First of all, we need to know definitions in acids and bases. 2, we need to know conjugate acid-base pairs, right? And to know how to tell the difference. 3, we need to realize what substances do we know as ampholytes, but how do we see in a given reaction? We don't just say them in general. We need to say them in a particular reaction, unless the question is asking in general. Yep, so that's the one. That's the one, guys. So those are the highlights. Please revise these issues that I'm highlighting so that you know, because this is where most of you get lost in the subject. Okay, acid rain does not cause damage in two lakes that have rocks containing limestone, which is calcium carbonate. Right. I like the fact that we had to know what limestone is by heart. So this means we needed to know these words and the respective chemical formula. You guys are given everything. You are babies in the sciences, right? Well, maybe you are because, yeah, in many ways you are babies in the sciences. But in many ways you are the big ones because you know better, you know more, and you are fast and quick, you are clever. We were not that clever. We were the mechanics. We had to mechanically concoct the chemistry, the apothecary. Is it the apothecary or is it the apothecary? Or is it the apothecary? Do you read Romeo and Juliet? You don't read those ones because you read nonsense anyway. Let's go on. Hydrolysis. Oh my goodness, that's the word. Again, guys, revise hydrolysis of salts. This topic has been occurring repeatedly from 2022 as I started to do some serious work on chemistry for you guys as matriculants. It has been repeated every time to this day, the hydrolysis of salt. So I told you the hydrolysis of calcium carbonate results in the formation of ions which neutralize the acid. And what are those ions? OH minus ions. Because a base, for it to neutralize an acid, it has to somewhat produce, or at least should be hydrolyzed into hydroxide ions. That's the one. That's the one. So these are the ions. So the examiner here is trying to push you around by just saying ions so that you don't know which ones. This is again to suggest that, guys, let's know hydrolysis of salts so that we can know exactly when this salt is hydrolyzed, what do we get? And again, the salts that actually change pH in many ways is salts that are either acidic or basic, because a neutral salt does not change the pH of water. It is itself at the pH of water. Right. So those are salts that come from complete neutralization. Right. Again. So please, guys, revise this topic. If you know it, good. Check in the box. But if this is not clear, please go back and study it. And you will see in the channel, almost every time I've done or treated a question paper of chemistry, I have always highlighted this topic. And it has been recurring for this past 4 years now. Yeah, 2022, 3, 4, 5. This is the 4th year now, so it's gonna still be there. Trust me. Okay, so we are done here. So we know the story. So 7.2.1 asks, define the term hydrolysis of salts. As I said, go back to acids and bases and revise all definitions and make sure you have a way of remembering them. Rather understand them, because when you do, you will always be able to generate those definitions. Trust me. But of course, you should be someone who reads novels, because if you don't read novels, your English is going to choke under pressure. But if you read novels, you'll be able to talk, even if you talk nonsense strategically. As you can see, sometimes when I don't know what to say best, I just talk a lot of nonsense nicely, because then the intention is to confuse my mark, to feel sorry for me, to go and make an argument with the examiners, so that they can just decide, just give a mark there. He's tried. So you don't just give up, guys. You try, even when you're trying in a nonsensical way, but let it be strategic. Let it look smart and, informed. You can't just give up and just throw in the towel. You will lose in life. And who knows, what if that little, pity mark for your effort would have been the one that makes you get a distinction, and you end up falling short because you just give up. Don't do it. But doesn't mean that not giving up, you're not going to lose, but just know you're just not giving up, actually. losing or winning, you just don't give up. And I promise you, you will never lose if you don't give up. Even when you lose, you're not going to be depressed and cry about it. You'll just know the strategy didn't work. You try again and try better. Right. What does hydrolysis of a salt means? It is a reaction of a salt with water. Hawu madoda, H2O. Khawufana ucinga ayiselula nansi into ufumana 2 marks yonke. Yes, amanqaku amabini for nje imbodana encinci kangaka ngumgcana ayona ngumgcale ngumgcana nje umqodlwana nje wombhalo ukunikeza amanqaku amabini. Hayi man, sanusiqhela nina 1 mark lento le. Gezisa abantwana nibenza bacingela uba bayayazi iscience bengayiqondi. Funeka bayikhuphule ematyeni le science. I-science ifana nokutrena kwejoni, uyikhuphule ematyeni uzoyazi. Hayi nje uyinkathelo ugqiba uhamba usithi uyi-scientist uzasihlekisa ngabantu. Anyway, whatever. I know sometimes I talk nonsense without thinking about it. It says now, explain with the aid of the relevant hydrolysis reaction how limestone neutralizes the thing. Now again, guys, in limestone, which one is the base? Because this is, calcium 2 plus ions plus the carbonate 2 minus ions. So this is the one. So which one is the base here? Now again, revise these polyatomic ions, which you learn in grade 10. I don't know if you still do. We learned this in grade 10 in the so-called ionic reactions. So we had names of this: sulfate, sulfide, nitrate, nitrite. We needed to know all of these things, dichromate, permanganate. We need to know these things, guys. So revise these ones. And of those polyatomic ions, we need to know which ones can be hydrolyzed in water further and which ones cannot. For example, the sulfate ion cannot be hydrolyzed, right? But the carbonate ion certainly is the one, because calcium 2 plus ions cannot be hydrolyzed. So this is why we're not going to choose them. So basically here we will write that basically what happens is the carbonate 2 minus ions that are the base here, plus water, because we said it's a reaction with water, guys. We go forward. What do we get? Now, we know that water becomes an acid this time. It protolyzes that dude, because water is an ampholyte, isn't it? So when it is given a chance, it acts like the big boss. Now what happens? We get here HCO3 minus, okay? And what do we have left? The hydroxide ion. This is the dude we're trying to showcase. That technically is the hydroxide ion that we're talking about. Of course, this is aqueous solutions, because water is a liquid. So what can you say? Nothing. This is aqueous. This is aqueous. Of course, you can say liquid. It's a liquid, but then it behaves like an acid according to Lowry-Brownstedt theory, because it will protolyze. So you don't have to show the arrow of protolization here. Just write the equation without that arrow that I wrote. I'm just explaining to you. So we can say, since this produces the hydroxide ions, we can say since the hydrolysis of the carbonate ion produces the OH minus ions, it will therefore neutralize. It will therefore neutralize the acid. It is like that, Mos. You see, we were told to show some equation. Now this equation, Balanced or not, it doesn't really matter, but key is that we should know that it forms this. In fact, it should be balanced actually. Let me not even impart nonsense into you. It has to be balanced, because if it is not balanced, it doesn't make sense. Right. We cannot analyze anything in that equation if it is not balanced. So now we then gave the explanation that this presence of these dudes will then be the only way we can neutralize an acid. So how many marks here? 3 marks. Wow. I thought it was going to be 2. So this means this equation, and perhaps balanced as well, that should be 2 marks. And of course, the left hand side is a mark, because we needed to know which ones are reacting together. So we can say here the mark is for the left hand side, because we know it's the carbonate ion reacting with water. That's exactly what it is. And then the right hand side, knowing that we're going to produce the hydroxide ions mainly, and explaining now that the presence of these dudes, because that equation alone, like someone who doesn't know something will be like, what? So what? Because you see, you must answer so that there is no so. Like, yeah, I feel it now. Make someone inspired to do chemistry, even if they were not chemists. If you can explain to someone who's not a chemist in such a way that they can see the light, just know you are there. You are where you should be. Okay, it says water in a certain lake has a pH of 5. Calculate the concentration of the hydronium ions in the water. That's easy. That's easy. We know that pH is minus the log of the concentration of these oxonium ions. So this implies that 5 is equal to minus the log of the concentration of the H3O plus ions. Now remember, this is a logarithmic equation. So what is the base when it is not indicated is 10. Now we reverse this to the exponential form. But then it is such that this becomes the exponent. We reverse it using the logarithmic rules. So this would imply that we've got 5 is equal to the log of the concentration of the H3O plus ions to the minus 1. Ne? Yeah. Then we reverse this thing nicely. I'm just taking you through the maths actually. So the base takes the position of the base, right? And the exponent takes the position of the exponent. So this leaves the concentration of the H3O plus ions to the minus 1. Now, inverse operations. We don't want this to the minus 1. We know the gymnastics, guys. So we want to kill the minus 1. So we'll multiply by minus 1. So we raise it to the minus 1. And whatever we do to the other side. Maths must be balanced. So this implies that the concentration of our oxonium ions is going to be 10 to the exponent. We multiply the exponents. That's what we get. So therefore, the concentration of our H3O plus ions is going to be 1 times 10 to the exponent minus 5 mole per decimeter cubed. Is done, is dusted, finished. See, this is just some mathematical gymnastics. Of course, I decided to do this. Otherwise, we could just jump from this step right through to this one. I'm just showing you the maths, guys. Physics is mathematics. But mathematics is not physics. Dang, what is that? Yeah, it is what it is. Technically, we know most in physics, we're always gifted marks for writing the formula. We get the marks for the substitution and for the answer. Okay, the gymnastics are a means to an end. It's not a mathematical exam, but it applies maths actually. So no manga business here. Now let's go to the big one. So this was 7.3.1, 7.3. Yikes. Please ensure, guys, the numbering is correct. The reason why I'm fussy about it is because I know most of you lose marks because of carelessness in this regard. You label answers incorrectly even when they are correct. And the teachers should actually be mean, because it means you are not careful. A careless student is not very likable. Only a careful student is likable. But of course, the duty of a teacher is higher than just preferences. They have to drill whatever they prefer into you so that you become exactly what they like. Anyway, the question says now, the volume of water in the lake is 4 times 10 to the 9 decimeter cubed. What a big number there. Lime, so this is calcium oxide, is added to the water to neutralize the acid according to the following reaction. Nice and easy. Now the final amount of hydronium ions. So it already tells us that the acid is going to be in excess. And I like the fact that we are given the number of moles, because a concentration would be a nightmare for us if we were given the concentration. But of course, we'd still juggle it, but with some challenge. So the number of moles in the final solution is this one, and it is of the hydronium ions, meaning the resulting pH is acidic. Right. As you can see, calcium oxide is a weak base reacted with a strong acid. This is the strongest acid you can ever find, the H3O plus ion. Right, so we know that once we react those two, we form a basic salt. A basic salt which is going to be weaker than the acid. No, what am I saying? Don't lie. We're going to form an acidic salt which will have a resulting pH being acidic. And this is the story right here. But again, it could just be the fact that the acid was in excess anyway, even if we had a complete neutralization. But calcium oxide is a weak base anyway. Metal oxides, they react as weak acids. Remember that. Again, go back to the theory of acids and bases. Read it from grade 10, grade 11, grade 12. Then attempt questions from grade 10, grade 11, grade 12. You will then stick to more grade 12 past exam question papers. You will be the best. Trust me. I know this. Okay, we are to calculate the mass of lime that was needed. Okay, sorry, that was added to the lake. Okay, so we know that the concentration here is coming from 7.3. Remember, this is the major one. This is the umbrella. And of course, this is the higher grade question, which is going to beg some serious answers from us. So, well, we just want to know how many number of moles of calcium oxide reacted. And from this equation here, calcium oxide plus 2H3O plus, going forward, going back, to calcium 2 plus ions plus 3 molecules of water. Is it water or is it water or is it water? Now all we can see here, guys, is that 1 mole of calcium oxide reacts with 2 moles of the acid. So we can simply say now here the number of moles of the calcium oxide, because this is what we want, right? So number of moles of the calcium oxide. Now guys, I will teach you to adopt this shorthand, summarized but very focused approach. Now if we want to take it from the oxonium ions that we know, we will have to halve it to go back to the calcium oxide. It's going to be half. Now this is a constellation of very serious ratios and proportions that you have to do and cross multiply, but at this stage I'm not interested. In the exam, you should be already at this level where you can just look in the chemical equations and know exactly what to do. So what is this? It's going to be half the number of moles of H3O plus that reacted. Simple. Right. So in fact we can even write here reacted, because this is the ones that reacted. So nice. So this implies that the number of moles of calcium oxide is going to be 0.5 into, now what was the original number of moles? Well, we did not calculate them. Okay, so we need to calculate the number of moles. Now we know that concentration is number of moles over volume, therefore it means number of moles is concentration times volume. So we're going to take the concentration that we got here, which is 1 times 10 to the minus 5, and multiply it to the volume, which is what we were given as 4 times 10 to the minus 9, to the plus 9, right? And this whole thing we subtract this number of moles that remained. So this is 1,26 times 10 to the 3. Right, so that difference will give us the number of moles of the oxonium ions that reacted. And then we relate those that reacted into the number of moles of the calcium oxide that reacted. Take care that this is what reacted, hence we take the difference. Right, so therefore the number of moles of calcium oxide is whatever we get here, 0.5 into basically 1 times 10 to the exponent minus 5 times 4 times 10 to the exponent 9. This one we subtract 1,26 times 10 to the exponent 3. So I'm getting a very large number here, 19,370 mole. All right. Usually when the number is this great for number of moles, it's sometimes nicer to write it in scientific notation, but nobody actually cares. Some students may prefer to say 1,94 to 2 decimal places, because now we're pushing these digits out. Now we pushed how many? 1, 2, 3, 4. So we're going to say times 10 to the exponent 4. This one is positive when we push it out, but when we push it back, it becomes minus. You get it? So one can present the answer like that. It's not a big deal after all. So what are we trying to get to, guys? The mass of this dude. So this one was a very simple question. So we go on and say, well, the mass then, the mass of calcium oxide is going to be number of moles times the molar mass. Of course, you can write it like this or write the original formula. Sometimes it's just boring, you know. Sometimes it's just boring to keep writing formulas the way they appear. As long as you're comfortable, just write it however you want. But if you're going to write it wrong, then same again. But I wonder what would it take for a student to write a formula wrong. Really? So this is 19,370 moles into calcium is 40 plus oxygen is 16. All right. Therefore, the mass of calcium oxide is going to be the answer. So let's see, it's going to be quite a big number. 19,370 times, into 40 plus 16. Okay, the calculators are nice in that they can handle. So now, guys, I'm getting a very crazy number here. So I'm going to do the scientific notation here. The number I am getting is 108. So this is 1,084,000. So 1,084,720 grams. But of course, you can write it like that. It's okay. Nobody's going to punish, or preferably you just push those digits out and then you round off to 2 decimal places. So this is going to be 1,084,720 0, 1 comma 0, 8 to 2 decimal places, of course, times 10 to the exponent. How many did we push? 1, 2, 3, 4, 5, 6 to the exponent 6 grams. Now this one looks a bit safer, but there's nothing wrong in presenting the answer this way. Okay, so don't shy away from presenting it that way. Came out that way, give it. Unless someone says in the simplest form, now that would mean scientific notation there. But if there's no specification of how that answer should be, you just hoy it however you see it. Okay, great. Yo guys, I'm tired. Okay, this was the last question. Yikes, I was getting a bit beat. All right, so folks, this is very nice, very interesting, you know, all these things. So certainly general substitutions are very important, but this was a calculation on its own. Again, this was also a calculation on its own. The difference here was a calculation on its own, and the brackets were the calculation on their own, and using those ratios in general. So we get 3 marks there. And of course, calculating the number of moles, that's the 4th mark, right? Great. So here, formula 5. Calculation of the molar mass, that's 6. And that's 7. Nice and easy, guys. So as you can see, this looks long, but if you know how to summarize your work effectively, because again, it's a skill to know how to summarize issues and pieces of information. All right, guys, so this would be a very nice and very satisfying and tasty 20 marks up for grabs. So guys, please practice. Practice definitely does make one perfect, but at the same time, when you get stuck, revise. Don't think you'll just magically keep all of this information. If you don't revise effectively, you're not going to win. And how do you revise effectively? You do as I kept suggesting. When solving questions, don't think it's all about solving questions. Remember, this is a study session. So as you solve, you hit definitions and you realize, man, I am shaky with definitions in this section. You go and revise all those definitions. You can even do it back and forth while solving here, so that as you solve further, your comfortability with the subject starts to kick in, or to drip in, or to sink in, however you want to describe that state. And then of course you keep going through all these questions. You get stuck. By the way, how do I calculate the pH? Go to your textbook. Don't rush into training your brain to sweat. No. Grab that study guide, open it. Oh, it's minus the log of this. Hey, what is the mathematics behind this thing? What are the gymnastics now of making the concentration the subject? You go through all of that. You can even revise mathematics, logarithmic equations. Go for it. Then come back. Okay, now I'm happy. Answer that question. Then go to the last one. Okay, this one is a bit technical. What do I need? Sometimes you may just want to go and check a video that has been done, whether in my channel or any other channel that you prefer. Check, okay, this is the procedure. And then you check some past questions, or even in the section, just go and look at those examples, worked examples. Oh, this is how it goes. Okay, now let me try this one now, using all of this. You don't have to try it the hard way the first time. No, take it easy. Try it out. You will be surprised, guys, how well you're going to be with this, because I knew that torture is not the best way of learning. But you just change the game. Or you even move the goalpost. You don't have to, force everything. Just move the goalpost a bit so that you're comfortable. Then you know that, okay, your study session has been fruitful because you got to revise definitions. When we talked about hydrolysis of salts, you got to revise that. Now, in essence, by just sitting with this past exam question 7 here, you will have covered most of the work in acids and bases. Now, this simply means if you start reading properly now, again, from start to finish, you will already have a lot of stuff in order, and now most of the reading is going to start to make more sense than when you would have read it the first time without really understanding much. Then after this, guys, you take perhaps 2 or 3 past exam question papers, and this time you're not going to solve it the way you have the first one. This time you try to push yourself a bit, because you've got to push yourself. And when you don't know, you skip the question. You continue until the end. Then you check if everything is in order, looking at your notes and how your work is done. Sometimes don't rely too much on the memos, the official memos. Just don't. Try to use your textbooks to check if you are right or wrong, because that in itself is going to be some form of a research of finding information in the text and understanding the text, because the memo might be wrong. You never know. So you don't want to be confused by the memo. You want the textbook which you trust and which is what is used in your class. Then after that, then you can go for the memo and see if it agrees or not. Then of course, if there's a discrepancy, you can discuss with your teacher, your tutor, your friends. You know most. Alright guys, so this is how you study, and I hope you will just do well, because this nonsense of okay, let me not put it that way, maybe I'm too harsh. Sometimes I don't listen to myself and hear what I say, Sometimes my eyes become very wide when I listen to the videos. If I got, especially when a student is asking about a particular question, I want to make sure I go and watch what I said, and then I start to realize, oh my word, what ganja did I smoke to even say such things? I don't hear myself, guys. Maybe I'm a psychiatric patient. Maybe I need some haloperidol, just to calm me down, or maybe Ritalin. Maybe I'm too hyper in this regard of commentary and, bashing things. Anyway, it's because, guys, science is not something that we should be smiling about. In science, we should be taking each other to task, because for it to be perfect, we should not be complacent. Otherwise, our science is going to be very, very poor. And as you can see, we are just simply following whatever everybody else is saying elsewhere. We hardly come up with things of our own. So this is the problem. We have plenty of natural resources in this country. We should not be depending on the outside world for most of how we process these and how we use these and creating things. Now, a lot of technology is created using our raw materials because we are just useless in the science world. We just simply, conform to standards set by others. We don't actually modify these and push others around when we can. I would love for a day when we actually push people around with the science. Not necessarily in the wrong way, but just challenging the world the right way with knowledge, strength and power and ability, creativity, innovation. We need to be leaders, guys. Why are we trailing still? Is there something wrong with us? No. But something is definitely wrong with our minds. Our mindset is wrong. Because even the mindset of those who teach is wrong, because they emphasize on cramming exam guidelines. That's wrong. Okay? Cannot be telling students to cram so that they can pass. It's not about them passing. We actually don't want such students making it. I wish I could be something that can just influence this, like a witch doctor. Bathakathe bonke aba bahlanyayo. Balungise ingqondo zabo zisebenze kahle. Bazoteach abantwana into ebhadlileyo. Not nonsense. Cowardice. Why do you teach kids cowardice? And yet you claim to be brave. You're really joking, are you not? How will we have the strongest scientists if we create babies in science, liabilities in science? Because now teachers worry more about their kids getting distinctions. Whether these kids understand the subject, they can use it, they can reason with it, they don't care. Because they don't give these kids a chance to do so. They just have to reproduce a textbook or a study guide or guidelines, whatever that is. And that's wrong, especially in life sciences. Wow. I hate what I see and read and observe. That's why people are never going to know anything despite so much knowledge floating around freely, by the way. Anyway, guys, I'll talk and talk and talk until people get offended, which I don't really care much about. But what I care about is pushing people around with knowledge and challenging their knowledge and stance in the field of science, because many don't belong in it, but they're standing right there in front. Anyway, guys, goodbye. I'll see you tomorrow. Then, of course, I'll do a series of, the other question paper so that we can make this nice and palatable. Otherwise, goodbye for now.